Large language models, or LLMs, have made incredible strides in areas like reasoning and problem solving, but they still face significant hurdles with things like hallucinations, logical mistakes, and the inability to fix errors during complex, multi-step tasks. This research paper, titled Steep Test Time Scaling Law via Environment Augmented Generation, proposes a new framework called Environment Augmented Generation, or EAG, to address these issues. The authors, including Lingrui Mei, Shenghua Liu, and others from institutions like the Chinese Academy of Sciences and the University of California, Merced, argue that current methods, such as chain-of-thought prompting, aren't enough because they don't allow for real-time checks or corrections. In EAG, the model doesn't just generate answers in a single pass. Instead, it integrates with an external environment to get immediate feedback on each step of its reasoning. Let me break this down. First, EAG uses real-time environmental feedback. This means that as the model works through a problem, it can validate each reasoning step against external tools or data. For example, in a task like counting the letters in a word, the model might generate a step, check it instantly, and adjust if needed. This is a big improvement over traditional LLMs, which might plow ahead with an error and end up with a completely wrong final answer. Second, EAG incorporates dynamic branch exploration. If the model hits a snag or an error, it can explore alternative paths. Think of it like a choose-your-own-adventure story, where the model deliberately backtracks and tries different approaches based on the feedback it receives. This strategic replanning helps avoid getting stuck in dead ends and makes the reasoning process more robust. Finally, EAG includes experience-based learning. The model learns from successful reasoning trajectories, meaning it builds a kind of memory of what worked well in the past and applies that to future problems. This creates a cycle of improvement over time. The paper highlights how EAG differs from existing methods. While some approaches use tools for verification or generate multiple paths, EAG tightly integrates feedback with branching exploration, allowing for more deliberate and efficient problem solving. The authors tested this with their model, called a 1-to-32b, which is a 32 billion parameter model. On various benchmarks, a 1-to-32b achieved state-of-the-art results among models of similar size. For instance, it matched the performance of larger models like O1 on competition mathematics problems and outperformed comparable 32b models by up to 24.4 percentage points. One key figure in the paper illustrates EAG in action. It shows the model solving a character counting task, like figuring out how many R's are in the word raspberry. The model tests its approach, encounters issues like case sensitivity or import errors, and uses feedback to correct itself. This demonstrates how EAG enables interactive, step-by-step problem solving with instant adjustments. Another important aspect is the scaling law they observed. The paper includes a graph comparing model performance on the Math 500 benchmark against training data size. Their A132B model achieves high accuracy with fewer training examples than baseline models. This suggests that investing in environment interaction during testing provides long-term benefits, especially as tasks get more complex. The advantages of EAG grow proportionally with the difficulty of the problem, making it particularly useful for precise multi-step calculations and logical verifications. The authors provide a theoretical framework for EAG, explaining how combining environment interactivity with systematic branch exploration creates a new paradigm for reliable machine reasoning. This is crucial for fields where accuracy is paramount, like scientific computing or real-world decision-making. In the introduction, the paper reviews the history of LLMs and their advancements, citing works from Brown and colleagues in 2020, OpenAI in 2024, and others. It points out that while LLMs can generate intermediate steps to improve performance, they often fail in extended chains due to unchecked errors. For example, if an early step is flawed, it leads to compounding mistakes, as seen in studies by Yao and colleagues in 2023. Recent related research has explored external verification through tools and feedback, as well as planning methods like generating code-based plans or exploring multiple paths. EAG builds on these by adding the ability to learn from experiences and dynamically adapt, setting it apart as a more comprehensive solution. Overall, The analysis in the paper shows that EAG not only boosts immediate performance but also establishes a foundation for more trustworthy AI reasoning. By allowing models to interact with their environment and learn from interactions, it paves the way for handling increasingly complex, real-world problems that require precise and verifiable steps. This could have broad implications for applications in education, research, and beyond, where reliable multi-step reasoning is essential.